Dr. Dev.
Bolo.
Yes, sir. Please start the session. Your mic is off, I think I can see. Sir, your microphone is off. Sir, your microphone is off.
Oh, I am asking to you, Devashish, that Dr. Dev, that whether the time is already half an hour is gone and we should continue with that.
Time, no problem, sir.
No problem. Okay.
Yeah.
Thank you very much.
Thank you, sir.
Welcome to the 8th invited lecture in this ICACA ICACA 2021, and we're privileged to have Dr. Sanghamitra Dev. There is a delay, but can't be happened because there is just paper presentation, and paper presentation you have to the best paper to identify the best papers as well. So sorry for the delay on my behalf, Dr. Sanghamitra Dev, who is there, I know from the list of participants. She is a staff data scientist, Cheek Incorporation, I think I have pronounced it correctly, California, USA. And she works on problems related school and college education to sustain and improve the learning process. Her work involves recommendation systems, graph modeling, deep NLP analysis, data pipelines, and machine learning. Previously worked with data scientist, was also data scientist and Action Technical Laboratory, where she worked on a wide variety of problems related to data modeling, architecture, and visual storytelling. She is an avid fan of Python, has programming been programming for on this. Trained as an astrophysicist, she also holds a PhD in physics. She uses her analytical mind not only to work in a range of domains such as education, healthcare, and recruitment, but also the leadership style. She mentors senior students at her assessment, and also organizations in her own organizations, and coaches them from various fields to transition into data science. Sanghamitra enjoys addressing technical and non-technical audiences and conferences, women joining technical courses. She's passionate about diversity and has organized many women in data science meetups. Lastly, I must say, which you should be said earlier, the Dr. Dev has a PhD from Drexel University. He was a student of physics and also did on astronomical data modeling. He was also visiting research at NBI Copenhagen, research associate at Lawrence National Laboratory, and postdoctoral fellow at Argonne National Laboratory there. We will deliver his lecture. Title is Computer Vision for Beginners, though it is meant for beginners, but as I said in the abstract, it's much more on that. I think it should be addressed to all the researchers here. Over to Dr. Dev.
Hello, everyone. Thank you for having me. And hopefully I will not be falling asleep in my own presentation because it's after 10 p.m. here. So I will talk about computer vision, and I will go a little deep into a few of the topics. So can you see my screen? I think it's visible.
Yes, perfect.
Okay. So here is the outline of my talk. I will give an introduction and talk about some of the applications. After that, I will talk about convolution neural networks and some of the state-of-the-art deep learning classification models. I will go through a pipeline in PyTorch, talk about classification metrics, give like a little bit of an introduction to object detection, some metrics for object detection, and then do a summary. If I run short of time, I might just not talk about one of these topics, but you will still have the slides. So what is computer vision? The idea of computer vision is to make our computers be able to see. So they should be able to see, but not just see, also comprehend what's there. So it's not enough to say that, the computer understands that these pixels have these values, but it also has to understand that this is actually a picture of Abraham Lincoln. And these are some of the quotes by Fei-Fei Li, who is one of the leading researchers in computer vision. According to her, like understanding vision and building visual systems is really understanding intelligence. So I will now go into some applications, which, a lot of these applications we do see in everyday life. So first one I wanted to bring up was image search. And this comes up in Google all the time. And I think we, almost all of us use it. I used it several times to actually prepare this presentation. So if you go and you search for something and you click on images, you get a range of images on whatever topic you're looking for. It is driven by image similarity. So they do have a huge pool of images, and they have similarity computations happening in the background, and they show you the most similar image when you look for something. Another very important direction of application is healthcare. The final goal is to have your entire body be scanned, and not just with images, but also reports being prepared with where you use NLP, and all of this information gets centralized, and you can have all different kinds of cancer screening, disease diagnostics, surgical assistance technology, and all of this is, a lot of it is driven by computer vision, because you kind of need images on every part of the body to understand what's going on. But I also wanted to, apart from the general system of healthcare, I also wanted to pinpoint at one particular example. And this is an example of detecting diabetic retinopathy from images of the retina. And as you can see in the left-hand side, you have like the picture of a normal retina, and then you have a picture of a diabetic retina. And you can actually use classifiers to detect them really well. And this was one of the competition in Kaggle, and I have given the link here. This is a very important problem, because a huge number of people are becoming susceptible to diabetes, and correspondingly, a lot of them are going in a direction where they might have diabetic retinopathy, which can cause blindness. And it takes a really long time for a physician to actually look through the images, create a report that actually says that this has retinopathies. Whereas if there were automatic processes, this would happen much faster. And I would encourage you to go and look at this link and actually do this problem. They have codes with like traditional classifiers that solve this particular problem. The other thing that I did not mention, now that I've mentioned traditional classifiers, at the beginning of the talk, is I will mainly be talking about deep learning techniques. And part of the reason to do this is I have started working on computer vision, let's say, about 8 months ago. And what I realized is that the deep learning techniques are much easier than actually going through the traditional route and learning about like details about images. And so I'm mainly going to talk about deep learning. Next slide. Yeah. Another very important application of computer vision is education, and this is very close to my heart because this is what I work on my for my day job. And here I have listed a range of applications in education, but I'd like to pick one up. You can see this child who's drawing a picture of a rocket. Now think of a simple system that collects all the drawings of the kids in schools and then analyzes them and basically concludes that, this child is very interested in rockets. So then they send a message to the parent saying that this week your child is very interested in rockets. Why don't you talk to him or her or them about rockets, and maybe send some more content on rockets and astrophysics, so that the parents or other adults in the children's life are equipped to actually feed into the interest that the child is having. So this is a very particular case, and all of these other instances that I've put, like gaze analysis or uncovering learning gaps, creating a career paths, all of this is possible by collecting different kinds of data, part of which are images from students. The next application I'm going to talk about is like one of the most common applications of computer vision, and that is self-driving cars. Self-driving cars basically have cameras, radars, and lasers that allow them to perceive the world around the car. And cameras are a very important part of it. And here you see these videos of like a moving, not necessarily a car, but a moving vehicle through a street, and it's detecting different objects and figuring out where they are so that collision does not happen. And I will keep coming back to this application several times. Another very important computer vision application is generally mobile apps. So almost all of us have smartphones at this point, and once we have smartphones, we get to this phase where we are very lazy to actually type anything and upload. So what we'll do is we'll go in front of something, take a picture, and expect the app to give us the result. And that is a very common application. So here I've put in a few examples of that. People take pictures of food, and they could upload it for writing reviews, but they could also upload it to some kind of fitness app that tells you how much calories you have consumed and other aspects. The next example is that of like a structure. Somebody is studying and uploading an image and wanting to know more about that concept. You have another picture of a person taking the picture of a damaged car who would upload it for insurance reasons or for other reasons. And then you also have this picture where someone is taking the picture of a portrait to figure out who painted this and when was this done. And there are like millions of use cases in this space. And it is like one of the most growing spaces in some sense. So now I'm going to talk about like some basic computer vision techniques. There are others. I have only considered images. And so you have image classification, and I will spend most of my talk speaking about image classification. And then there is classification plus localization, which is, you not only say what the object is, but you also draw a bounding box around it. And then object detection, which is something I'm going to talk about a little bit, is also when you have multiple objects in the same image. And then instance segmentation is actually getting the pixels that are related to a particular class. Let me now go deep into classification. So what is classification? It is basically given a set of pixels for which you have some values. You need like some method of telling you what is in that image. And in this case, your model might come back with this has an 85% probability that it's a cat, 12% probability that it's a dog, 2% it's a hat, and 1% it's a mug. So you use this model and you conclude that this image is that of a cat. So that is the classification process. So what does like a typical computer vision classification pipeline look like? So currently the main structure of classification networks in deep learning looks something like this. There is a convolution, there is some kind of activation like ReLU, and there is max pooling, and then you basically put a few of them together and then put some fully connected layers on top of it, and that's pretty much your architecture. And then your final layer is your number of classes. Now, CNNs have been very effective in deep learning, in doing classification and other operations in computer vision. One of the reasons for that is they are really good filters, and they can effectively use information from adjacent pixels to downsample the image, and they're very good feature extractors. So I will go a little bit more into details about like the timeline of computer vision work. And even though neural networks have existed since the 60s, it's in the past decade that we have seen this huge amount of work that has gone into computer vision to produce some very state-of-the-art results. And the first was LeNet, which had like a convolution network in 1998. The next one was AlexNet, which produced the really good or really higher performance on the ImageNet data set. Then there were a bunch others. There was like GoogleNet, VGGNet, ResNet, and so on. I will talk about AlexNet, VGGNet, and ResNet because not only just because they're fairly common, but they are also architectures that are easier to understand, and they have performed fairly well on the ImageNet dataset. Any questions so far? Okay, I will move on.
Question will be asked at the end. Okay.
Okay. I will move on. So before going deep into the architectures, I wanted to give you a sense of like how the field has progressed. And even though you don't have time here, the x-axis is basically time with AlexNet being 2012, and towards the end, inception V4 is like 2017. And with time, the models have become like more complexities have been added to the models, and they have been made more like architectural changes have been made, and we have seen increased improvements in the accuracy on the ImageNet data. And I also wanted to give a glimpse of the ImageNet data. The ImageNet data is has a lot of variety. It has images of cats and dogs and squirrels, mammals, but it also has vehicles like rockets, aircrafts, watercrafts, and many other classes. So it's a very diverse data set. And it has been like the go-to data set for proving that the new computer vision model works, because that's what older models have been compared against. The other thing that I wanted to go into was the size of the models. Now, as you, in this axis, you see like the top one accuracy is in the y-axis, and then you see like number of operations in the x-axis, and the circles give you the size of the model. So here the winner is kind of, I'm not sure what the light blue dot is, but Inception the light blue dot is Inception V4. So the winner is Inception V4, but if you see in terms of size, ResNet 18 is a really small model, GoogleNet is a small model. So when you're actually trying to work on a problem, working with a larger size model is takes up a lot more time and a lot more cycles if you're working with GPU. So it's always better to start with a small model. And if you think that your problem requires more accuracy, you can go to the larger models. So that's one note. So let me now go into like the first of the models. And I will talk about AlexNet. So AlexNet is a network of 8 layers with convolution normalization, convolution pooling and normalization. This was new compared to what was done before, because previously these CNNs, stacking these CNNs were not common. And so it was pretty novel. And the other thing that was also fairly novel here was the use of data augmentation, where flipping, jittering, color normalization, and other kinds of data augmentation was done. And so the main gain, or the main new thing here was you had the ReLU normality and non-linearity, the max pooling, dropout regularization, and the GPU training. This is also when GPUs started becoming more available, and there was like more progress done in the hardware side. And it was a big moment in computer vision, because basically a revolution was underway, and it was like this new CNN network has arrived, and there's specialized hardware. Now deep learning can solve the computer vision problems. And this is the time when this was ready. So next one I'm going to talk about is VGGNet, and there were other architectures that have happened in between, and I just chose a few of them. So in VGGNet, what was special compared to AlexNet is that there were the convolution filters were very small, but because these were small convolution filters, it had fewer parameters, and you could stack many of them together. So they were much deeper. So VG16 had 16 layers as opposed to 8 layers in AlexNet, but the filters itself were much smaller. And this led to a much higher accuracy. It was a huge network. And the higher accuracy was certainly like a good thing. One thing that people become acutely aware at this stage is big networks are also expensive. They train very slowly, and they're also slow to evaluate. So even though like you are gaining in accuracy, in a production environment, a smaller network might be more favorable. Like that's a way to think about it. So before going into the next network, which is ResNet, I wanted to talk a little bit about vanishing gradients and exploding gradients. Now, as we've seen from AlexNet, and before AlexNet, there was just like maybe 1 or 2 CNNs, and then AlexNet had like 8 layers, VGG has 16 or 34 layers. So we're going in this direction where we just keep adding layers, and we expect that the accuracy would go up. What does that mean? If you had 200 layers or 300 layers, would your accuracy go up? And the answer to that is if you just take a simple layer, like if you just keep having convolution max pool normalization and keep stacking them up, eventually it saturates at a higher, and even though you have more number of layers, your accuracy might be lower. And that is what you see in the plots here, that the 56 layer network has a higher training error and a test error compared to the 20 layer network. And why does this happen? It's because when you have n numbers, and if you have n very small or very large numbers, your gradients can explode or they can become very small. So as you keep adding more and more layers, you basically give this opportunity for either vanishing or exploding gradients to happen. So ResNet came up with a solution at this time. And the solution was, let's skip 2 layers and send the result over. So what's happening here is, here you have an input. In the plain layer, here you have an input. You have like convolution, ReLU, convolution, and max pool, and you go on. But in case of ResNet, after 2 layers, you not only send the output of the convolution layer here, you also send the input. And this way you make sure that every 2 layers you're sending this information and your gradient is not vanishing. And this system can be stacked so that you have something that's 150 layers deep. And that was one of the models, like ResNet 150, which was one of the highest performing models. And this works. One example I wanted to show was a comparison between a plain 18 layer and a 34 layer network, where the 34 layer actually performs much worse than the 18, well, not much worse, but a little worse than the 18 layer network. But when you incorporate the ResNet architecture, the 34 layer actually works better. So here's ResNet network. What was novel is, being able to skip networks. It reduces computational complexity and number of parameters. It's kind of similar to like an ensemble of shallow networks. It won the next prize for next level of prize for the ImageNet networks. Now, this is where I decided to stop in terms of giving you details of the architecture, because after this, there is GoogleNet, there is Inception, and the architectures become fairly complex, where different parts of the architecture are connected in different order. And there is some math that goes behind it to prove that it's, this kind of connection actually provides more stability or better accuracy compared to the previous generation of model. But that is the idea, like you kind of keep changing and creating different kinds of links in the architecture, and the models eventually improve. And ResNet, starting from ResNet 18 to ResNet 150, like all of these perform fairly well. So next, I will go into the image classification pipeline, and I will use PyTorch as the framework. But you can use any other framework. You could work in TensorFlow, you could work in Keras, and you will pretty much get all of the tools that you need. PyTorch and Keras are more high level. Well, Keras is the highest level, and it kind of abstracts away some of the details, which makes producing code easier and faster in some sense. So here is the basic pipeline. I've written a little bit about data pre-processing because you need to move images to individual folders of each class into individual folders. It's a very tedious process. It's specific to images because unlike structured data or even text data, you cannot fit an image into like an SQL table or something like that. And then choose a classification model. For me, the go-to has been Resonant 18 just because of the size. And whenever I'm trying to do like a new problem, which I end up doing quite often, I choose like a smaller size model. And then you have two routes that you can go into. Let's say you only have access to CPU. What you can do is, and you still need to perform some kind of classification task. What you need to do is you need to make sure that your layers are frozen and you can extract the features. Once you have the features of the images, you can put any kind of classifier on top of it, like a logistic regression or an SVM, and train your classifier and then measure your performance metrics. Typically, like if you have enough training data, fine-tuning does result in a model that's more accurate and that's more tailored to your specific use case. So the direction of fine-tuning is something like this. There is, you first do your data augmentations, like color corrections, cropping, rotating, and other data augmentations. Make sure weights for the layers are not frozen, because in this case, you're using the architecture, the pre-trained architecture, and you want to initialize it with the pre-trained weights. But then as the model keeps learning from your data, the weights need to change. After that, you add the final output layer. It could be a softmax, it could be a linear layer. You choose your optimizer, which can be Atom or SGD or anything else. And you train until your accuracy and loss on validation data converges. And finally, measure your performance metrics. Let me give you like a brief view through the code. So typically, I mean, I make this point every time I speak about any classification problem is make sure you divide your data into train, test, and validation. And dividing your data into train and test is very common, but people forget validation very often. And this is important because while training, you use your validation data and tune the different parameters in the model, and like keep repeating that process. Whereas your test data, you never touch it during training. And then once you're done with training, you use your test data and you get your metrics. So make sure you have all these three. Here I've put some numbers for the division: 72% train, 8% validation, 20% test. These numbers could keep varying. Like it could be 90% train and a smaller amount in validation if your total data set is really large. And here I've also given some code which from scikit-learn, which you can use to basically get this kind of train, test, and validation data sets. Next thing you do is data augmentation. Here I've given like one example of data augmentation. You can see this cat, and this image is rotated, cropped in different ways, flipped, and these are like some of the output of the data augmentation process. The nice thing about data augmentation is that basically from one piece of training data, you're able to produce 9 pieces in this case. Another thing to remember is when you're doing the data augmentation in your code, you don't need to do all of the augmentations for your validations and test sets. You only needed to do it for the training set because the others are mainly used for evaluation. The next part I wanted to talk a little bit about is, again, moving and loading data. So the moving data part is simply like Linux statements. They're just tedious. And for loading the data, you have to make sure you load it into the right environment. So data sets is something that PyTorch uses. And then the data loader basically loads these different train, test, and validation sets. And this is very important before you start your training process. Now for training, now you see I have some code in orange at the left-hand side, and these have mainly gone out of my screen. And they're basically the default code for PyTorch. And the main things to remember while writing this function is that you want to make sure that if your mode is train, it's only then that you're changing your model or updating the parameters. Whereas if you're in the validation mode, you're always evaluating. And then once like this is the trained model, but you also have to make sure you choose the right pre-trained model, extract the features, put in the right classes, put in the loss functions, and basically schedule your put your learning rate and schedule it. Here in this particular case, I've made sure that the learning rate goes down by a factor of 0.1 every 7 epochs, so that you reach initially you take larger steps and later on you take small steps. And then depending on how much time you have, you can choose, you will train the model and put the number of epochs. This is pretty much what the code looks like for your deep learning model. Any questions? Any questions?
Nothing now. You will continue.
Okay. Next slide. The other thing to keep in mind is pre-trained weights, whether you want to freeze it or not freeze it. Typically for feature extraction, pre-trained weights are frozen. And if feature extraction can be very important if you're doing similarity-based measures. For instance, the image similarity, image search example that I gave, if you're trying to build something very simple, you could use pre-trained weights and create like a search engine for yourself. For fine-tuning, the weights should not be frozen. So having a function like this and setting it before you start your training process makes sense. So now I want to talk a little bit about classification metrics. These are not tied to computer vision at all, but since I've spoken about classification, it's important to know how to evaluate your results. So these are some terms that are quite generic. So true positive is number of observations that the model correctly predicts to be the positive class. False positive is number of observations that were predicted to be positive but are not. And similarly, the opposites are false negatives and true negatives. And precision, recall, accuracy, these are like really important metrics that you should always measure in your classification task. So precision kind of gives you what percentage of the positive class is actually positive. Recall, on the other hand, tells you what percentage of the positive class actually gets captured by the model. That is, can you, your model could be really good, but it might not get all of the information from the data. And it depends on the problem you're solving. You could be solving a problem where getting it correct is more important than getting a prediction on all of your data. And it could be the other way around too. Accuracy is important to measure, but it's also important to remember that it could be misleading, especially if you have unbalanced classes. So your accuracy could be 90%, but then let's say your class imbalance is such that you have 95% of your data in one class and 5% in the other. Then if you predicted that all of them belong to the 95% class, your accuracy would still be very high. So always look at precision and recall along with accuracy. Also look at numbers per class. So your classification problem might not always be binary. So just check everything per class to make sure that your performance is where you want it to be. Another important metric to look at is the confusion matrix. And here I've shown like a picture of the confusion matrix of a multi-class classification problem where basically images of different kind of foods were taken and then the classes were predicted. And here you see like there's apple, banana, bell pepper, and so on. And ideally what you expect is that the number is high along the diagonal, but it's like 0 everywhere else. But classes are typically correlated. So you will see that one class gets confused as another class. So for instance, apples get confused as tomatoes, which is probably not surprising. Or onion and ice cream, onion and ice cream, it seems, get confused quite often. And then ice cream gets confused into all other classes. So this gives you a good sense of some classes which are very tight, like green salad, but then some classes which are very fuzzy, like ice cream, which is very difficult to identify from this data set. So it's a nice metric to look at. The next thing I wanted to talk about was thresholding. And in binary classification, if your classes are more or less balanced, then 0.5 is like the threshold, which tells you like if it's less than 0.5, it belongs to one class. If it's if the probability is higher than 0.5, it belongs to another class. But basically, when your probability is closer to 0.5, it means your model is very confused and it doesn't know which class it belongs to. So you can keep a decision threshold. You could say that if the output is less than 0.3, then you will give it one class, and greater than 0.7, you'll give it another class. And between 0.3 and 0.7, the model does not know what to do. So if you build a system like this, what would happen is that part of your data would have probabilities in the range 0.3 and 0.7, which means this data does not have any output, which means your overall coverage will go down. You won't be able to predict on all of your data. You'll only be able to predict on part of your data. In this case, basically, you sacrifice on coverage, but you improve on your accuracy. Okay, I think I have some more time. I have basically not spend a lot of time on object detection, so I will just define the problem. I will not go into the details of the model. So for object detection, YOLO has been like a state-of-the-art program codes or paper, however way you want to put it, and it performs really well. The nice thing about YOLO is that there's a really nice GitHub repository, and you can download the data. They have a train.py, and they'll kind of tell you how your input needs to be structured. The structuring is different from the classification problems. But once you go through those steps, it's like a very few steps, and you get to a nice bounding box. And the name is YOLO, or you only look once, because it is like a one-shot learning process where the model predicts the coordinates of the bounding box and the probability of belonging to the class together. And because it does that, like it takes one pass at the image and does this prediction, it is much faster than any of the previous models. And here I've put in this image again of like that was relevant to a self-driving car, because this kind of operations are what self-driving cars really look for. Is, you have a camera that looks outside, you have to detect an object and say what kind of object it is, and it has to happen very, very fast because the car is moving. So I would encourage you to look into this. If not anything else, like look into the code, download it, and just play with it a little bit. Another important point that comes up is, now that we are detecting objects, how do we measure that we have done a good job detecting the object? And here a new concept comes in where it's called intersection over union. And basically what it means is you take the area of the overlap in the numerator and divide it by the area of the union. So if your detected box and your actual object, that is your ground truth, do not match exactly, then the area of the union will be higher and the area of the intersection would be lower. Typically, putting a threshold of 0.5 is very common. That is, has to have 50% overlap for it to be accepted as a detection. Another important metric that people look at is average precision, which is the area under the precision recall curve. And once you average this across all your classes, then you get the mean average precision. And these are like two metrics that are looked at very often when you're doing object detection. I also wanted to give you like an example of like an object detection case where maybe your threshold is 0.5, but for the same object you get IOUs of 0.53 and IOUs of 0.83. It makes sense that you will take the bounding box that has a higher intersection over union ratio. I think that's all I have. I wanted to summarize saying that a lot of advances have been made in computer vision in the past decade. And that is really good for us practitioners. We can just take advantage of all of the research that has been done and most of the codes that are available. And the main thing we have to do is collect good training data for the problems that we are trying to solve. And in general, unless like you're a computer vision researcher, it makes sense to use a pre-trained model before trying out like some architecture of your own. Success of a project is very closely related to defining and measuring your metrics correctly. So make sure like, if you're doing a bounding box, you know what object you're trying to pick up. So for instance, here I have this example of this cell phone taking the image of plants. And the goal here is it'll take the image of a plant and then your app will tell you what kind of disease the plant has. So in this case, like the bounding boxes should be around leaves of the plant. So that definition ahead of time is very important. The other thing is programming frameworks such as PyTorch and Keras has made coding in this deep learning space much easier. They have abstracted away a lot of the details, which means you can get to a space where you're actually creating a model in a very short time. So I think, yeah, that's it. Thank you.
Thank you, Dr. Shangamitra Dev, for your excellent presentation. Dr. Dev introduced computer vision right from the first principles, then discussed and described architectures, models, and also about computer vision systems that are transforming the workplace through its emerging technologies like artificial intelligence, deep learning, and allied areas, and also the pose certain challenges and solutions in our lecture. Dr. Deb also introduced the term that some of the codes and metrics and many lessons are to be learned, and indicated some of the research areas hitherto unexplored. Any question from the participants for the conference? At least we can take one or two.
Hello.
Yes, Dr. Debashish Dey.
Yeah. Madam, you have mentioned about YOLO algorithm.
Yes.
So how, what is the response? Whether is real-time operations possible? Means real-time mobility management.
So I am not sure if specifically YOLO is used for the real-time management, but there are definitely models that are doing real-time object detection constantly. Like as the cars move, they keep taking their cameras all around and they keep taking the pictures and object detection is being done. I'm not sure which, like if YOLO is used or which version of YOLO is used. It's also possible, like, so the companies that work with computer vision and self-driving cars develop their own algorithms. So there's a very good chance that every company probably has their own proprietary algorithm to do it.
So YOLO Lite is also used in IoT application. YOLO Lite, you know that.
Yeah.
It is very much used. So
it's, yeah, I would say it's definitely possible, but I don't know if the self-driving cars that are actually out there are using it or not.
Yeah, especially in the CCTV cameras you are showing, na? CCTV cameras, whether they will be using this kind of.
Yes.
Okay. Thank you.
Thank you. Any other question that I can take right now, because you are getting delayed, and Dr. Deb also asked the students or the participants to ask at least one question in the middle. Any question?
Yes, sir. I have a question to ask. Are you hearing me?
Yes, you can. I am.
Okay, sir. I wanted to ask to Madam, is there such as the object detection? I mean, that is the radar and the lidar. Whether we use radar or the lidar in an outdoor environment. There is an indoor environment and outdoor environment. Whether we use the, I mean, the computer vision also in the indoor environment.
So
For localization purpose, for navigation purposes.
As long as you can take images, so whether if it's an infrared camera or however way you're taking the images, as long as you can take images, object detection is possible. But you need a certain amount of light to reach the sensors to make sense of the data. So
Yes, madam, I know that there are multi-sensors, multiple type of sensors, such as UWB, RFID. I mean, the RFID is used for low power communication purposes, as well as
so
the
if you can take a video if you can take a picture or a video, you will be able to do object detection on top of it.
yes. I mean, that is the sliding window. Yeah, madam. I mean the sliding window, madam.
I am actually not sure what you mean by sliding window.
No, I'm saying that I wanted to differentiate between the computer vision as well as the I mean the indoor localization in an indoor environment. I mean there are different types of communication, wireless communication system. Through these, we can use the multiple sensors. I'm saying that whether
Sure. What is your question?
yes, my question is that I mean for the outdoor environment, we use the radar. Yeah, am I right? Such as radar as well as I mean such as the object.
So I mean, radar is a form of sensor.
Yes,
I
sir,
mean,
is a type of sensor. I mean that is used just as suppose that is the camera. I mean that is the camera as well as through a camera or the radar we actually detect the object. Object may be any type of object. I mean it will be a type of car or vehicle.
so again, as long as
Are
there's
you
a
asking
camera
about the
pointed,
applicability of radar in an indoor environment, or is there any other parameters or any other areas that to be looked into? Indoor, I think your question may be restricted, or rather, the differences between the outdoor and the indoor. Is it so?
Yes, yes, sir. Actually, I'm saying that outdoor environment is actually used for the, I mean, computer vision actually used for the outdoor environment.
And
Computer vision.
will it hold good for the indoor environment? That is the question, possibly. I don't know.
Yes,
Madam,
main question is that simply is that to the madam that we computer vision, especially this, there is a term, I mean, that is the sliding window, which is specifically used for that.
so I think if the question is if computer vision techniques will hold indoors, the answer is yes, as long as there is enough light to actually capture an image, or you could also do it with infrared images or other wavelengths. As long as you can capture enough photons into the camera sensor, some kind of computer vision technique would be applicable. But specifically, I'm not sure what your question is around radars.
Thank you very
Okay,
much.
thank you, madam. Thank you,
Yeah,
madam.
thank you, Dr. Dev, for your excellent presentation. Thank you once again. That's close. For the session is over. Over to Dr. Dev for the next session.
Thank you.
Thank you.
Thank you, Dr. Dev, for your nice presentation and for giving you time at almost at the midnight after 10 p.m. Thank you very much. Now we are starting. Yes, thank you, madam. Now we are going to start our next session. I can see our friend Mike Hinche, Professor Mike Hinche is present. So can I see Professor Ambod Dotto?
Amber is here or not? Then
Hello?
Nilanjana is here.
Yes,
Amber is
Yeah.
Yes,
please,
actually, Mr. Dr. Nilanjana, madam, can you please introduce?
Yes, sir. Yes,
yes.
sir, I'm here.
Yes.
Yes. Yes.
Yes, sir. A very good morning to everyone present over here. Today is the second day of our conference, ICACA 2021. We are very honored to have with us a very eminent guest, Professor Mike Hinche, President of International Federation of Information Processing and Chair of its Technical Assembly. He has also been the former Director of LERO and Professor of Software Engineering at the University of Limerick. Professor Hinche was previously Director of the Software Engineering Laboratory at NASA. He remains as a consultant to NASA. He is the founding chief editor-in-chief of the NASA journal, Innovations in Systems and Software Engineering, launched in 2005. His work with NASA was implemented in various space projects and will be incorporated in future missions. Particular areas of software research for Professor Hinche include formal methods, autonomous system, and software reliability. We request Professor Hinche to grace us with his kind words. Over to you, sir.
You are muted. Mike, you are muted.
Good morning, everybody. Apologies for that. Very good to be with you all again, and thank you for the very kind introduction. I'd like to speak with you today where the topic of this conference, of course, as we know, is advanced computing and applications. So I'd like to talk to you about an application area of advanced computing techniques. And this is specifically space exploration, which is something that's very hot in the media and on social media in particular at the moment. This is partly, I guess, because we'd like to see something a bit different from our humdrum lives in various lockdowns throughout the world, but also because there's been a lot of success recently in space exploration. We've seen the SpaceX launch to bring humans back to the International Space Station. We see multiple countries, including India, have missions to the moon and to Mars, and a number of successes recently in terms of that. One of these, of course, is the new rover Perseverance, which has landed on Mars and started working and started sending back pictures, etc. This, of course, is building on the success of previous rovers, a long-term plan for understanding a lot more about the Martian planet, about the conditions there. We do know many of the things about it, but there is a belief that there was water there at some point. Potentially there still is some water in places, perhaps under rocks and underground. And this would be a great confidence booster in the fact that there had been life at some point on the planet. Not necessarily intelligent life, but we won't know that until we find out a bit more. The rover itself, of course, has been sending back images already. It will collect materials. It will send back materials from the planet. What it plans to do is actually quite ambitious, giving us a lot more information about the planet that we've never had. And of course, there are plans to launch a helicopter, Ingenuity, and you've probably seen that plans have already started with that. The idea of the helicopter is to demonstrate that we can actually fly devices on another planet and in the harsh conditions of Mars. Remind you just how variable Mars is. If you stand on the planet's surface, your feet will burn, but the liquids inside your head will freeze. So that is how strange the planet is. It goes from burning to freezing in roughly 6 feet. So the idea of this helicopter is to demonstrate that we can fly devices on another planet. And then, of course, those devices would be used to collect information much as the robots do, but with much more accuracy, with greater amounts of data, and much more flexibility. So the intention would be, for example, to send swarms of devices that can collect data. And the estimates are that these devices could collect as much data in a day as all of the rovers on Mars have done in all of the years that they've been there. So very ambitious, but huge payback and huge returns is successful. So the idea is that the helicopter will collect data, feed it to the robot, and of course the robot will relay that back to Earth in various ways and with various assessments and validations done in advance. 2024 is the year that has been set for the Artemis mission. Artemis, of course, named after the Greek equivalent of Diana, goddess of the moon. And so this here you see is the Artemis heavy lift, the SLS, or the device that will bring materials, etc., to the moon initially and ultimately onto Mars. At least that is the intention. This has had various names over various years. It's been known as Constellation, a very uninteresting name. It's also been known as Ares, Ares being, of course, the Greek equivalent of the Roman god Mars, the god of war. and the capsule that would bring the humans is known as Orion, after the constellation of the Hunter. So this is the technology that will ultimately bring us to the moon and onto Mars. But the intention, of course, is to be able to collect so much more information about both the moon and Mars before we get there, and before we bring humans back to the moon and onto Mars ultimately. So this is a chart from the NASA controller. The controller is the chief financial officer of NASA. And what it does is chart the cost overruns of various missions and projects with the effort put into requirements and planning beforehand. So if you look at this, you'll see that when NASA invests a small amount in its requirements or pre-planning, say in the region of 2 to 3%, it has cost overruns of about 200%. Conversely, if it puts in a substantial amount, about 15% of its program costs into the requirements, then the cost overrun is something more like 10%. Now, each of these red dots corresponds to a mission. The names have been taken off just so it's readable. It's not secret. All of this information is publicly available. This dot here in the center is the Hubble Space Telescope, for example, one of NASA's most successful missions, not a human mission, but still one of its most successful. I believe that this curve is accurate in terms of its shape, but it probably should be up and to the right. And the reason it should be up and to the right is that NASA missions typically overrun about 800%. So it's very difficult to plan these sorts of activities. It's very difficult to cost these sort of activities. But the emphasis here is that when effort is put into the planning, the cost overrun is greatly reduced. And that is very, very significant for something that's going to cost huge amounts of money. It's estimated that the original plans for Artemis were that the cost of the software would be in the region of $8 billion US. That's without any of the hardware, that's without any of the science that needs to be done. It's just the software. That would make it the largest software project in history. And if that largest software project in history were to run 800% over budget or even 200% over budget, you can see the significant losses that there would be. So we're talking about building some of the most expensive software ever, in this case, the most expensive software ever. And we're talking about software that has to run for long periods of time. The Navigator software is the oldest software that's known, the oldest software in the world, still running, we believe, even though it's gone interstellar. So this is something similar. We have to have software that will run long term, but can be updated. And that is one of the great advantages of software, is that we can make changes to the mission even after it's been launched. The big advantage of software is that it does facilitate change as long as that change is done correctly. And we can make changes to the behavior of the mission even after the physical devices have been launched and have gone so far that they could never possibly be retrieved. However, there are requirements for huge amounts of autonomy. These missions need to be able to work very much by themselves, to protect themselves as the main reason, really, because the dangers of things that were not foreseen, that were not planned for, that could happen, that could arise, that we never even dreamt of, means that the software will have to be changed to protect the mission, to make sure that it continues to work, and to try to ensure longevity. So this means that a certain degree of autonomy is required, and in this case, it's very high levels of autonomy. And we'll talk a little bit more about that. The consequences for failure are dramatic. Typical missions are 20, 25, 30 years in planning. The mission we're talking about of going back to the moon and onto Mars is something that will probably be 50 years in the planning. That's not to say that parts of it will not be achieved before that, but we're looking at long, long periods of time working on this. If we were suddenly to lose the mission or suddenly have it severely damaged that it couldn't continue, then we have lost that amount of work, not only a lot of money, but an awful lot of human effort and input and timing. The consequences are also very great in that we lose public trust. The public pay for space exploration in terms of taxes. So we're talking about the loss of taxpayers' money, but we're talking about the loss of support, the loss of morale, the loss of public belief in space exploration and the space exploration process. And space exploration has a great role in furthering other technologies. There is a law in the US, an act of Congress that requires NASA to use all of its investment in technology in areas other than space exploration. So people associate NASA with space and monitoring other planets and space travel, but in fact, NASA spends about a little over half of its budget monitoring the Earth and protecting the Earth. But all of the technologies it develops, whether for Earth monitoring or for space exploration, needs to be used in some other way. So there is a requirement that all of the technology is used in other areas. So, for example, there's been a lot of work by NASA as working on the notion of IP in space, so that spacecraft, satellites, etc., could be nodes on the internet and use the internet for communication. This, of course, has great applications to the Internet of Things, great possibilities for the Internet of Things, that we could have not just devices connected to the internet here on Earth, but we could have devices connected to the internet in space. And there has been great success in that area. It at the moment is using an intranet rather than the internet, but essentially the principles are the same. Much of NASA technology is used in other areas. We had a very interesting talk just a few minutes ago about image processing and image recognition. And of course, this is an area where NASA has done a lot, because NASA has taken so many pictures from space, so many pictures of the Earth using satellites, etc. And of course, has been working on the automated analysis of these pictures and these images, and trying to determine how the Earth is progressing, what issues there are for us in terms of pollution, etc. And of course, monitoring more specific things like deforestation, pollution, etc. So all of NASA's technologies have a role somewhere else. And as I say, this is a legal requirement that the technology can be used in areas other than just space exploration. So for 20 years or so, I've been working in the area of swarm technologies. When we started working on this, this was something very, very new, very, very dramatic. And in many cases, people just didn't believe it. The idea is to be inspired by nature, to look at swarms of bees, flocks of birds, colonies of ants and termites, and to see what they do and to be inspired by what they do. So we don't want to just copy what they've done or what they do, because in many cases we don't know exactly how they work. We have ideas about pheromones, about trails, about communication. We think we know how flocks of birds communicate and why they follow in particular patterns when they have to travel in the wintertime and when they migrate. But we don't know for certain. But we do want to be inspired by some of these things, because in many cases they produce great benefits. So the idea of using swarms has been used in a whole range of areas. I have a colleague who works for Johnson & Johnson, and he tells me that this has meant that drug discovery has been reduced from an average lead time of about 17 years down to about 3 to 4 years. So that's very, very significant, particularly nowadays as we're looking for vaccines, etc. So there are many advantages to using swarms in that context. For communication systems, swarm technology has also been very beneficial. It's been used widely in video on demand and similar technologies. For environmental monitoring, I already mentioned that NASA spends more than half its budget monitoring the Earth. So environmental monitoring, checking for levels of pollution, checking for our water, checking under the sea, under the seabed, and in fact, under the Earth, has all been areas where swarm technologies have been used, and particularly in exploration. So we've used swarms for exploring in the sea, in lakes, under the earth, and of course in mining. But of course, my interest is in using it in the application to space exploration. So the idea is that in future, we won't just use one spacecraft, except for situations where we have to, like the heavy launch to the moon, But once we get to space, that exploration will be based on a number of smaller spacecraft. And by spacecraft, I mean anything that flies in space. So it could be something like a space shuttle or a miniature space shuttle. It could be something like a rocket, but equally, it could be something like a robot or a rover, or that does fly in space. And the idea is that instead of using one large device, we use a number of smaller devices. So we can better use solar power. Battery power has always been a major issue for NASA. And in fact, about 25 years ago, NASA set up a prize of $1 billion for anyone who could develop a battery that could run for 24 hours, charge for 24 hours, and run for 24 hours, etc., without memory loss, as the problem is called, without loss of the power of the battery. And after 25 years, nobody has claimed that prize. So battery power continues to be an issue. So more effective use of solar power is the big asset. Access to areas where large craft could not go. There are certain places where we cannot send large spacecraft. And in particular, I'm thinking of the asteroid belt, which I'll talk about, because there would be too much collision with that spacecraft, too much damage to it. And even a little damage would be unfortunate and could mean that the entire mission was put at risk or even lost completely. We want to be able to do more complex things. So for example, if we want to be able to take X-rays of something, we need to be able to position two devices at opposite sides. So in one particular mission, which I'll talk about, we're interested in collecting data about asteroids. We're interested in taking X-rays of asteroids. This means positioning two spacecraft directly opposite each other with the asteroid in between. But the asteroid is moving. The asteroid is moving at speeds and directions that we don't know and can't predict. So we need to be more agile. We need to be able to move position, change position much more quickly. So basically, we want more accuracy. We want to be able to collect better data. We want flexibility. We want speed of response. We want to be able to collect a lot of data. And as I mentioned, using something like a helicopter on Mars could collect in a day what the rovers have collected over a period of years. Won't be able to collect physical samples as the rover is planned to do this time, but we still would be able to collect huge amounts of data. But what we want is resilience. We want these missions to be able to survive by themselves in a very harsh environment and over a long, long period of time. Because of the amount of planning that has gone into it, we don't want to send something that will be lost after a few months. We want something that will last for years in space. So we've been working for many years now on a concept mission, and it's a concept mission because it will change dramatically between the initial concepts and launch. The original launch was to be this year. It's been postponed, but much of the technology is already being used in a host of other areas, both on Earth and in space. And much of this technology is actually being used in the helicopter that you've seen on Mars. So this mission has 3 submissions, one to go to the surface of the Moon and Mars, one to go to the rings of Saturn, and one to go to the asteroid belt. So Lara, the submission that will go to the Moon and Mars, probably is going to bring us the greatest results in the near term. But PAM, the prospecting asteroid mission to go to the asteroid belt, is by far the more complex and the one that embodies most of the challenges and most of the technology. So it's the one I tend to use for my examples. So we're looking to use devices that look something like this. So these devices are essentially rovers, if you like, or robots. Each of the nodes is a computer, and at each node, control is made by passing the control from one node to the next. So if you like, the device works by falling over. It can expand and contract using nanotechnology and nanomaterials, and it can climb over craters and rocks, as you can see here. And we can connect a number of these devices together. Of course, can carry materials, devices, rockets, etc. So this is all very nice as an animation. Here's the real thing. So as you can see, it expands and contracts. This particular device can shrink to be a 30 centimeter cube. It can expand to be 2 meters tall. Again, moves by essentially falling over by changing its center of gravity. And this particular device can also climb the outside of a 5-story building. It doesn't work as smoothly here on Earth as it would do in the lower gravity of Mars. But it gives you an idea of how it works. So the intention is to send one large spacecraft, so a large rocket, a large device, to L1. L1 is the Earth-Moon Lagrangian point. It's a point in space where there is essentially no effective gravity on bodies that are small enough and light enough. And we're talking about bodies, devices, spacecraft, if you like, that are roughly the size and weight of a laptop. Think of it like that. The idea is that 1,000 spacecraft are launched from this point, L1, and then they're pulled solely by gravity into the asteroid belt. So getting to the asteroid belt is done without any power, so no battery, no fuel, just pulled by the forces of gravity. It takes roughly 2.5 years to get there. The devices, when they get there, form themselves into a number of subswarms or subgroups based on devices that they carry. So they carry cameras, X-ray devices, magnetoscopes, etc. And these are used to identify asteroids of interest. And of course, the asteroids of interest are based on input from space scientists who are looking for specific properties and specific information about various asteroids. And this data is collected, and a ruler for each of the subswarms would then send that data back to Earth. You see here, the arrow marked 5 is unidirectional. So this data is sent back to Earth, having had some amount of pre-processing on it, but there is no control back from Earth back to the mission out in the asteroid belt. And the reason for this is it's just too far. The distance is so great that even if we could send a message from one of these devices back to Earth saying there's a problem, and even if Earth could send instructions for how to overcome that problem with no delay, by the time the message was sent and the response sent back, there would have been 40 minutes past. So there's a 40-minute round trip delay, and the entire mission would be lost by the time any sort of instructions could be sent back. So this mission has to be completely autonomous in space. It has a number of issues. We expect a number of the devices to collide with each other, to collide with the asteroids, because we don't know exactly where they are. We know the path of the asteroid belt, but we don't know the exact position of exact asteroids. So there will be a lot of collisions. And in fact, we're sending 1,000 spacecraft in the belief that 60 to 70% of them would simply be lost because of collisions. When there is a collision, a device may no longer be useful. A camera may be damaged, can no longer take pictures. What can we do? Well, what we can do is we can have that device change its role, because we can change its software. And by changing its role, it can take on a different role. And so that may be, for example, data processing, or it may be communication and helping with sending data back to Earth. The other problem is solar storms. The sun is a star, and like all stars, it has stardust, which sounds romantic, but basically it's space junk. And every now and again, the sun ejects this junk. It also ejects radiation, and this can be damaging to the devices. So these devices have to be able to go into a sort of sleep mode so that they're protected and not damaged. And then when the storm has passed, we take them back out of that sleep mode and they restart. The big advantage is that we know about 24 hours in advance that there is going to be a storm, because the sun changes color. And we can either monitor that from the asteroid belt, or we can monitor it from Earth, because there is enough time to send a warning signal. Again, 40-minute round trip delay, but we have about 24 hours notice. So I'm going to play you part of a video which describes some of this mission. I'm going to skip the first few minutes of it just to save a bit of time. But the idea again is to launch these devices into the asteroid belt and to collect data autonomously and to protect the mission autonomously.
A 1-meter cubic package, manufactured using super miniaturized autonomous reconfigurable technology, or SMART, will contain all 1,000 1-kilogram spacecraft. This SMART cube will be delivered to the Earth-Moon L1 Lagrange point for deployment. Each spacecraft will be released in sequence from the SMART cube. The self-deployment of each spacecraft from its SMART shell will be the reverse of the manufacturing scenario. After deployment, the recyclable SMART shell will reconfigure into a stackable and reusable rectangle for return. Carbon nanotubule tethers will be deployed from multifaceted MEMS nodes to form the frame for the sail. The lengthening-shortening process is completely reversible, and the nodes are flexible. Thus, the frame is extensively shapeable. A SMART instrument and subsystem holding platform, similar in design to the space frame, will be reconfigurably tethered to the frame. The sails will reversibly deploy over the frame from specially designed MEMS nodes. Sail and frame are changeable in shape and extent, and are capable of forming tip vanes, making holes, and stowing sails as needed to assist in navigation and data collection. There are 10 classes of spacecraft specialists, identical except for their specialties, including 8 instrument classes or workers, plus communication specialists called messengers, and processing specialists called leaders. Subswarms will form and depart as groups of 100 spacecraft become available, with 10 from each specialist class. Over a period of 2.5 years, the swarm will travel on a solar sailing trajectory toward the asteroid belt. In each subswarm, imagers will perform remote detection of asteroids. Based on imager input and mission goals, leaders will select optimal targets. Each subswarm then navigates to its assigned target. Imagers collect data for a 3D model from stereo imaging, with possible inputs from other worker classes for further details near the target. Once the 3D model is adequate, clusters of workers of the same class move to optimal configurations for their data gathering operations. When leaders determine that the target has been adequately surveyed, data-taking operations cease, survey knowledge is shared, and a messenger is selected to return the data to Earth. Meanwhile, the subswarm moves on, the imagers initiating the search for new targets. All subswarms are simultaneously detecting, selecting, surveying, and searching for new targets. As a result, over the course of the mission, hundreds of asteroids will be studied.
The first time I played this video in public was at a space conference a number of years ago, and I was the first speaker in the conference, and at the end of my talk, somebody stood up at the back of the room and said, "I'm glad to see that we're starting this conference with science fiction. In fact, this is anything but science fiction. All of the technology for this does already exist. We do need to make it better. We do need to make it more efficient. We do need to make it a lot cheaper. But some of this technology is embodied already in the helicopter that will fly on Mars, Ingenuity, and that will collect the data from there. The intention, of course, is that ultimately multiple devices would be sent to Mars to collect data, and again, also to other planets. We've gotten a lot of publicity from this over the years. This is a posting from New Scientist, a very respectable scientific publication, as you know, from 10 years ago, where they picked up on details of a number of patents that NASA had filed on this technology. Unfortunately, some of the space geek websites misunderstood what we were talking about, and so on social media a lot of discussion went about us trying to do some damage and to self-destruct to do damage, but in fact the intention was the very opposite. We got some very good positive descriptions from the Times of London, for example, that devoted almost an entire page to this technology. And in fact, we also got a lot of publicity for the fact that my late mother at 81 got her first patent on some technology related to this. I actually overheard her talking to one of her friends on the telephone, telling her about what it was I did with NASA. And of course, what she was describing was completely wrong. But then I thought about it a bit, and we were able to adapt some of what she described and turn it into a number of patents. This is her receiving her first one. And in fact, that first patent is being used in the helicopter on Mars. So we've been actually working in a number of areas in computing that contribute very much to this. A few of these areas will be well known to you, and a few of these areas are commonly used in all sorts of applications, but we're just bringing these four together in various ways. So formal methods, which deals with the correctness of software and of course hardware also, but in this case software. Autonomic computing, which takes inspiration from the human body. Software product lines, which allows us to develop a number of self-similar software systems, taking ideas from physical product. And automated code generation, which, as you know, is to many people the holy grail of computing, where computers write their own code. So we've been working on a project called FAST, Formal Approaches to Swarm Technologies, to look at how we can describe these kind of systems, not just for space exploration, but a swarm-based system in general. Because the advantage of the swarm is emergence, that we get additional behavior that we haven't actually pre-programmed into the system. And this is really important in this type of mission that has to be able to protect itself in a harsh environment. But just as in the area of AI, we want to be able to describe the range of possibilities that we'll accept from this system. We don't want to be able to let it do just about anything. So we have to be able to constrain the behavior in some way. So the result of this project has been to describe something like a dashboard of different notations, everything from CSP, which is Hoare's language of communicating sequential processes, that deals with describing behavior of items or processes that are running in parallel, to WSCCS, which is weighted calculus communicating systems, which brings in probabilities and the likelihood of particular events happening, to X machines, which is dealing with the changes in state in these types of systems as a result of actions and decisions that are made. One of my postdocs has developed a language called ASSL, Autonomic System Specification Language, that is particularly designed for these kinds of systems, that allows us to describe fluence or long-running properties that give the things that we need for this type of application. The big advantage is that it's formal or mathematical, so we can prove properties of the programs that are written, but also it generates Java. So Java is not used in flight by NASA, but it means that we have code that is executable as well as a formal description that is amenable to mathematical analysis. In autonomic computing, we take inspiration for the human or mammalian body, and particularly the autonomic nervous system. So the sympathetic nervous system is concerned with fight or flight. That's the short-term protection of the body from various stimuli or intrusions. And the parasympathetic nervous system, which is the long-term rest and digest, to ensure the body has enough rest, enough food, enough energy, etc. So from this, we've been able to build up an autonomic environment. We use the concept of a heartbeat signal, as in embedded systems, to indicate that something is working. And so in other words, it's alive. We add to this the notion of a pulse beat, which in the human body, the pulse can tell us a lot about the health of the body. It's running too fast or too slow, etc. So NASA has actually used this idea for about 50 years and called it beacon monitoring. And the idea was that a signal would be sent with a simple data source, but it would be sped up or slowed down or intermittent to indicate various states of health of the system. We can put components into sleep mode when there's danger or when they're not working correctly. So in the case of a solar storm, we can have them in sleep mode so they're not damaged, and then we have to wake them up again afterwards. We can have components stay awake or wake them up again when it's safe for them to continue working. And we can do a negotiation between components within the system, what we call an autonomic license, or for short, an ALICE signal, that allows components to work together to trust each other. So this has implications for cybersecurity as well. We've used the idea of feature models in particular from software product lines. The idea is that we're going to use essentially the same technology in different guises. We're going to use something like helicopters on Mars. We're going to use something more like the tetrahedron I showed you earlier that will climb over rough rocks and craters on the moon. We'll use devices that fly through the rings of Saturn and through the asteroid belt. They all have different issues, even though they're based on much the same technology. So the core software can be the same, but we do need to change it for different environments and different platforms. So here you can see, for example, in red, the self-protection mechanism, which is to protect the devices going through the asteroid belt and dealing with the concept of a solar storm. When we go to the moon, we don't have the problem of the solar storm, but we do have the problem of storms and dust storms on the planet. So there will be a different form of self-protection for the helicopter at that point. And we've worked for a number of years on technology, a new form of technology for code generation. The idea being that many of the requirements for systems in general, but in space exploration in particular, are based on describing scenarios or use cases. In NASA, these traditionally have been based on natural language, more recently on things like UML, etc. The idea is that if we can generate appropriate models of the system, we can use typical existing code-generating tools. We can extract from models from code using existing reverse engineering tools. But if we take the mathematical laws of concurrency, so essentially the laws of relationship between processes put running in parallel, and we can reverse these, we have a form of round-trip engineering. So we've built the tool for this. It's using a combination of things we've written specifically for it, things that are used using existing tools that are out there in the public domain, either for free or in some cases quite expensive. But the idea is that we capture scenarios described by engineers, and ultimately we generate a model using a theorem prover. And from that, we can analyze the behavior of the system before we generate code. We were able to use this in a number of ways. We can automate the entire development process, as I say, completely round trip, from requirements to model to code and back again to requirements. We greatly improve the quality of that code. We can do proof of properties and on implementations, which is very, very important to us. We can do proof of correctness. We can demonstrate that our software is fit for purpose before we even launch. We can do a form of requirements analysis, a sort of a what-if analysis by changing scenarios and seeing what the resulting behavior is. And we guarantee the correspondence between the requirements and the implementation of code. And this is an area where automated code generation has failed in the past. A number of the commercially available tools generate thousands of lines of code that nobody can justify. So in our situation, we can guarantee that our requirements are met in the implemented code, and we have licensed this technology to one of the major tool vendors for code generation. We've used this for automatic end-to-end code generation of a provably correct system. We've been able to re-implement systems automatically after we make changes in our requirements. We're able to re-exploit this across platforms. People forget NASA doesn't use typical processors. NASA has most of its processors custom made to be low weight and low power. That means that when it develops a new system and a new platform, it often is doing it for the first time and nobody else has used that platform before. So being able to regenerate code on different is very important. We're able to reverse engineer legacy systems to sound models. Again, a lot of the code is quite old by the time the mission launches. We want to be able to understand what's going on and to improve the quality of that code. We want to be able to document code as well of existing systems. And in particular, NASA uses expert systems for controlling satellites. And many of these expert systems are very old, no original documentation. And the people who've worked on these systems have long since retired. So we've been able to actually document some of the rules in expert systems using this technology. And more importantly, we're able to take old software and re-engineer it to a much better and more efficient implementation, often on a new platform. So far, we've used it in a number of agent-based systems. We've used a number of wireless sensor networks. If you like, you can consider the ANS mission to be a wireless sensor network on steroids. It essentially is the Internet of Things, but is the Internet of Things in space. And we've used it for verification of the robotic procedures of the servicing of the Hubble Space Telescope. The Hubble Space Telescope, for those of you who are not familiar with it, is probably the most successful of NASA's missions in recent years. It is roughly the size of 3 buses. It is the most powerful telescope in existence. It will shortly be decommissioned and replaced with JWST, the James Webb Space Telescope. The original intention was that the Hubble would come down every 5 years for servicing, that it would have a number of updates to it in terms of battery power, in terms of lenses, etc. Unfortunately, it was designed to fit exactly inside the Space Shuttle cargo bay, or in fact, I should say the other way around. The Space Shuttle was designed that the Hubble fit exactly in its cargo bay. There was a problem, however, when the telescope was first launched and that its folding solar panels didn't work. These had to be replaced by fixed panels, and as a result, it no longer fit in the cargo bay of the space shuttle. So the mission to service it had to be done with a robot. Actually, in the end, it was done with a combination of a robot and astronauts, but the original intention was to do it all automatically with a robot. And these are the instructions for the robot servicing. It's roughly 5,000 pages. If it looks like a Word document, there's a good reason for that. It is a Word document. The first column here is timing constraints. The next column is the movement of the grapple arm, or the large robot arm. And then the next two columns are the dexterous arms, which is the smaller part of the robot. In the end, the dexterous arms were replaced by astronauts, but the large part of the robot was still used. The problem is that the battery on the robot only ran for 8 hours and then had to be recharged. There were also points where we could not see what was happening. We could see what was happening based on using 3 satellites, but 11 minutes every 90 minutes, there was a time where you could not see anything. So nothing critical could be done during these 11 minutes. Unfortunately, the exact timing of the 11 minutes wasn't known until the mission had already started. So these 5,000 pages of instructions took about 5 years to develop and needed to be regenerated within hours after the mission launched. The big advantage of a Word document is that we can tag it, we can produce XML, and we can then feed it into our tool, which is the code generator. The idea is that what we can change these instructions into this internal notation, which is actually CSPM, so a machine readable version of CSP that describes parallel and concurrent behavior. And what we're able to do then is generate Java from that. So what you can see here is our tool reporting a deadlock. And it kept doing this the first time we tried to use it on these 5,000 pages of instructions. And we put it down initially to the fact that this was a prototype tool and not something to worry about. But in fact, the problem was that there was an error on the first line of the 5,000 pages of instructions. Now, we're not saying that we wouldn't have found those by other means, but it was very satisfying that our tool was able to find these problems so quickly and so early. So again, the goal is to go to the moon again by 2024 and ultimately to bring humans to Mars. A lot of technology has to be developed in the meantime. A lot of information will be captured by things such as the helicopter flying on the Martian surface, which will demonstrate that we can indeed fly on the surface of other planets. And some of the technology that I mentioned to you here is already being used in that helicopter and will be used in future missions. So we have a long way to go, both physically and in time and in terms of aspirations. There's a lot we need to develop further and better, but we've made a number of steps towards building resilient systems for space exploration. And of course, we're using technologies developed by computer scientists and engineers all around the world, with focus on a number of areas that we see as being beneficial. These missions, of course, involve thousands and in some cases tens of thousands of people working on different areas. I just have to be working in the area of the software. So a word of warning that I like to give to people is that not everything scales up. Just because we can solve one small problem doesn't mean that it will scale up to a huge problem. So here, just because we have a solution on paper, it doesn't necessarily scale up to the Artemis mission. Thank you very much indeed for your attention. Thank you for your invitation again to join you. And I hope the next time it'll be in person and not virtually. And I'd be glad to take any questions. Thank you.
A very big thank Dr. Hinchley for your insightful lecture on the topic building resilient autonomous space exploration missions.
Thank you.
It is indeed a very insightful lecture, and all the participants of the event will enriched with your exciting lecture. Mr. Hinsley introduced the resilient space exploration system initially, and then he focused on various swarm technologies and its application areas. And his main focus was on space technology. Then Dr. Hinsley described what the coordinated swarms of smaller spacecraft offers. And then he described about the autonomous nanotechnology swarm and ANTS concept mission and demonstrates with the help of various videos. So we are very, very thankful for your very resourceful lecture, Dr. Hinsley. Now I ask all the, if there is any question to ask Dr. Hinsley for this one. Anyone of the audience can have any kind of question to Dr. Hinsley.
No? Okay.
Okay, thank you, Hinge.
Guess not.
Nice talk, Mike.
Thank you very much.
So once again, is there any question? So Dr. Hinsley, you had a plan to send this technology to go to moon by 2024, right?
That is a stated date by the government. I'm not so sure that it's very practical, but if enough effort is put in and enough budget is put in, maybe it is.
Okay. So so if there is any further question, anyone from the audience, any participant have any kind of question?
Can I ask a question?
Yes, sure.
Thank you, Mike Hinche, for your exceptional presentation. I like to
Thank
ask,
you.
our university also collaborated with NASA Stephen Center, and in 2019, I was part of a project of multi-agent learning and swarm intelligent technique design. But those projects mainly we need to do with OpenAI, that is not developed by NASA, because most of the technologies that we need to develop software, it is not openly available to work on. As you also described in your presentation, that those are highly licensed and outside NASA, they cannot use that. So what are the main technologies that the researcher can use who are not part of NASA, and they can explore multi-agent learning and swarm intelligence?
Well, obviously NASA is a US government agency, so the technology is made available to US researchers ultimately. Because it is funded by the US taxpayer, it is made available to US agencies, to US contractors, to US citizens, but on a licensing basis. And the basis of the licensing depends on the application. So for example, academic researchers can use much of the technology for free. Companies would be required to pay for a license because they cannot be seen to be getting a benefit over other companies based in the US. The technology can be licensed overseas, but again, it can't be given free to people overseas unless it's given free to people in the US also. The government cannot be seen to be given preference to a company or an organization that's outside the US or that is going to get a benefit over other companies or organizations. But the technology can be licensed. That is possible. There are certain technologies that are embargoed for licensing overseas, but that the justification for that has to be made. Those embargoes, or ITAR as it's called, typically relates to technology that can be used in weapons rather than technology that can be used for good. You could, of course, make a case that some of this technology can be used in weapons, and therefore it could be a situation where it's embargoed. But yes, the technology can be licensed and can be used. Not always straight away, of course.
Thank you so much.
Any other question from the participant? If no, then once again, thank you, Dr. Hinchley, for your exciting and insightful lecture on the topic. And we believe that you always extend your support in future also to us.
Indeed. Thank you very much for the invitation to join you. I appreciate it.
Yes. Over to Dr. Debashish De.
Thank you.
Dr. De, are you there? Yes.
Thank you, Mike. I think there was his maybe absent.
Okay.
Thank you,
So, Dr. Mondol, you just take care of. Yeah.
Fine. Thank you, Dr. Amar Datta and Nilanjana, for your nice conduction of this nice program of Mike, who is a good friend of me. And thank you, Mike, for your excellent presentations and information about the future trends of NASA. So that is one of the biggest challenge you have taken, and then I think hopefully this will be benefited for the society, particularly for the societal need, and definitely all of the researchers will also be benefited with your enlightenment of this type of computations and future trends of computations. So I think this concludes the session. Thanks, Mike, again, and I want to love to invite you again in our program. You are integral part of our program at Kolkata. Time and you are a good friend of us. One of us enjoy your association in any occasion, any form of occasion. Thank you. So I think the Aniruddha Nag is there. I am just handing over to Dr. Aniruddha Nag for the proceedings of the next session. Aniruddha, you are here.
Before starting for the next, I always like to congratulate Mike. In spite of difficult time zone, he has always attended our conferences. Mike and CSI has become synonymous. Thank you, Mike. Namaskar from our side.
Thank you very much.
I really feel amazed at how you can manage your time, because you are so busy, but whenever we just want to have you, you are always there with us with a smiling face.
Well, I do my best.
You are the best, no doubt about it. You need not to do best.
You are part of Kolkata. You are now part of Kolkata, and we are missing you physically. We are missing you physically last 1 year.
Yeah. Mike, let me tell you one thing. We are preparing an e-book, and there I have seen your photo. That is a computer that will be inaugurated by Professor Dr. J.K. Mondal today itself in the valedictory session. I have seen your photograph, and I have seen now Mike has defeated time. You are the same Mike with a smiling face. We're so proud.
Okay. Thank you.
Thank you, sir.
Okay, once again, thank you. So can we now conclude this session now?
Yeah, please.
Yes. So thank you, Mike, once again.
Okay. Aniruddha, proceed for the next session.
Yes.
Yeah, I'm there. Amber, thank you.
Yes, thank you.
After a long gap, probably 2 to 3 years, I have seen you.
Yes. Okay.
And you have also defeated time. You are the same person, the same Amber. The same.
Okay, I will contact you later, right? Okay.
Yeah.
Sure.
In the next session, there is a video presentation. I will request Mr. Shamurjit or Dr. Tufan to say something or to introduce that whether the video presentation session, how many video presenters are there or something of that sort. Please.
So I would request Shamurjit sir, who is also present in the session.
Okay, Tufan, you can carry on.
Okay, sir.
Just
give
check it
us a few moments, everybody. Just get the thing. Aniruddha sir, as of yet, there is no videos present in the session. Sir, are you there?
Yeah, I'm there.
So, sir, we have no video presentations for this session. All the papers that have been presented as of yet have already been presented physically.
So we can conclude this session and we'll prepare for the
Here.
lunch. And
Yes,
after
sir.
lunch, we'll meet again.
This session, and the next session is from 2 p.m. So we can activate the link from 1:45.
Thank you. Thank you all. Thank you for.
Thank you all.
Thank you for. Bye.
Okay, thanks.
Thank you, sir.
And